submit things. This is probably a bad day to ask. We have so many people out. But who here does not have a calculator like this? I mean, a physical one that you could use. Okay, just one person. I posted on Canvas this thing which is called Second Midterm Review Sheet, which is just, well, you should note the first line says everything on the first midterm review sheet, so that's also posted. So I'm kind of drawing a line. Today, Thursday, will be the last day we're going to have anything that could be on the exam, which is on the 9th. It'll be the following week after next. So you have any questions? Or you want to come see me in my office hours about something on here? All good. Today, we're going to talk about optimization, which is kind of a general term. It's optimizing something, making it better, or making it as good as it can be. And it could be minimizing something, or it could be maximizing something. It could be more complicated. Like, for example, you might want to maximize your free time while you're here. Or you might want to maximize the amount you learn. Or you might want to just maximize your GPA. Or, I don't know, if you're looking way ahead, maybe you want to maximize your future income. And I mention those things because they all kind of sound good, but they're in conflict, right? So, sometimes it's not like one variable you want to maximize. Sometimes there's something intermediate or related. You might want to maximize your happiness. Well, that's kind of vague. I mean, which of these would maximize your happiness? I guess, is your immediate happiness or your long-term happiness? So, these are not, of course, these are like sociological problems. We're not going to deal with them here. We're going to deal with math problems. I guess my point is there are various ways to to optimize things, and mathematics is not always the easiest or the best way. You need to have a good model that you're using, and sometimes the best way is doing experiments. So that brings me back to, I want to talk a little bit about soap bubbles for a minute. I guess if I had gotten here earlier, I'd set this up. It's going to take a minute to get here. So if you have soap bubbles on wireframes, because of the properties of soap bubbles, mainly surface tension, the surfaces tend to minimize themselves. So that that surface that I showed you so many weeks ago, where we had hyperbola, the surface area of that hyperbola was in some sense a the minimum surface area. All right, let's see if I can find this. Now, this is an example of something where you wouldn't want to do the math. You could, but I think this is the commercial. They're going to show us a commercial.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message.
We're just going to take a quick look at this.
Right, so here we are at the bubble tank, which is filled with a wonderful bubble mixture and these wireframe shapes. Now normally, when you blow a bubble, the soap film forms the smallest possible surface area to contain the volume inside it, and so you get a sphere. With these though, we can start to do the same thing, but with some boundaries involved. So if I take this cube, dip it in the bubble mixture, when we pull it out, the soap film will attach to the boundaries here and form the minimum surface area to connect them all together. So the soap film is calculating the minimum surface to join these edges. And if you then start to change it, so let's take out this boundary, it will adjust to the new minimum area. And I'm going to come in and I'm going to break that one. Look at that. Maybe I'll take out. And we have all these other shapes. You can try putting in the tetrahedron over here. So if we dip that in the bubble mixture, we will get this minimum surface area. So it's linked all the boundaries together at a single point in the center. And in fact, if I remove one of these, you'll get that new minimum surface area there. Actually, if I take that one out, we might even get a nice, there. Is that it's a saddle point of some description. Someone will email me and correct me on that. And at this point, you can go crazy. We've got all different shapes. Each one will give you a different minimum surface arrangement. So that's the minimum surface area for joining those edges. And if we wanted to calculate that, it would take ages and be a very involved calculation, whereas the soap film just relaxes straight into that minimum solution. It's absolutely incredible. And as always, I'm going to break a few of them to get a slightly more exciting surface. There we go. That is my favourite one. An interesting extra thing you can do is if you take the cube frame, you put that in, and you start by getting the minimum, there is the minimum surface area for the cube, you can actually make a few changes to the middle by adding in an extra bubble. So I'm going to try and catch another bubble. There we go. So now I've got an extra cube. That central bubble, instead of being a sphere, because of these extra bits of soap film, its minimum equilibrium shape is a smaller cube. This particular shape is what a three-dimensional projection of a four-dimensional hypercube would look like. So there, with bubble mixture and wire frames, you can make four-dimensional bubbles, and that's fantastic.
Everyone asks.
Okay. I don't know if that was fantastic, but at least was pretty enthusiastic about it. So again, sometimes mathematics is not, calculating something is not the best way. Now, optimization often comes up in science in terms of scientific principles. And I wanted to mention something just because most people hear about string theory. I'm supposed to do this. I'm supposed to do this at the beginning. refraction title. Most people have heard of string theory, and aside from its some kind of, well, it's not that brand new, but it's like at the edge of physics. Most people don't really know what it is. I don't pretend to really know what it is, but what's interesting is it starts at a very interesting first principle that involves optimization, or in this case, minimization. So the idea is, before string theory, and actually the current accepted theory, because string theory is far from accepted, you had little particles, electrons, protons, neutrons, various other particles, mu particles. There are all sorts of particles that fit into a theory. And string theory posits that there are actually all these little kind of vibrating strings of different sizes and different vibration frequencies. Well, if you think of these particles as moving through time, what you have is, you have like a surface, which is like a cylinder. And if you take a kind of a cross section here, you're just going to see, a string. But if you have an interaction between two particles, what's going to happen over time is, like here, you might start off with two particles, and then one of these particles might give off another particle. Again, what the cross section looks like here is we've got one string, now we've got a little extra string as something branches off and combines over here with the other particle. Now, all this is really unimportant. What's significant is that the principle behind string theory is that these surfaces are minimized. They're optimized. And, string theory is a big mathematical theory at this point. It can fit with what we know about physics, but it doesn't predict anything that we can test at this point. So basically, we start with this idea here, and we add a lot of mathematics using that principle that we're minimizing these surfaces, and then you get all these other interactions that string theory posits. Again, I don't know if we have any physics people here, but that's fine. Even if you were a physics person, the chances of you, until you plan to go off and get a PhD, you're probably not gonna be very interested in string theory. But we hear about it all the time. So, okay, another place in physics we run into this minimization idea is I think people are a little more aware of. You have some kind of surface, like the surface of a piece of glass, and you shine a light ray at the glass. You probably know that the light ray goes through the glass, but it changes angle. We talk about the index of refraction of the glass. One of the really interesting features of this phenomenon is that when the light is going through the glass, it's actually going slower. This is just light in a vacuum, or just pretty much how fast light goes through air. It goes at this value, the speed of light in a vacuum, often called c in physics. But as it goes through the glass, it's going to go through the glass at some fraction. some smaller value. And what's interesting is that you can figure out this index of refraction knowing the speed, because it appears that it obeys this law that says the time to get from point 1 to point 2 is again minimized or optimized. If the light were to shine straight through here, it would go through more of the glass, and it would slow down, and it would take longer to get there. It's like somehow understands exactly how, where to hit the glass, so that the distance in time from here to here is a minimum. So again, another example where in science we need to minimize or optimize some feature. Right. I want to talk about, again, very briefly about something off topic, which you may have run into in high school. Not every high school math class covers this. It's a topic called linear optimization. And the idea is you have some variable that it's modeled by some equation. Right? In this case, we're going to have some variable z, which is modeled by 2x plus 3y. And we want to optimize this, maybe minimize it or maximize it. And we have some constraints. So, for example, we say x has to be greater than or equal to 0, y has to be greater than or equal to 0. And then maybe we have some other equations that we can use to constrain these variables. X plus 6y greater than or equal to 24, y greater than or equal to -3 plus x, in this example. So the strategy to solve this is we graph these inequalities. Right? So 3x plus 6y, let's see, x is 0, 5 is 4, and if y is 0, then x will be 8. So, and we're looking for things that are greater than 24, so this is going to be this area over here. For this guy, I guess I will just draw in his intercepts are 4 and 2, 4, 6, 8. And again, it's this area here. So the places we're interested, and I guess when we get to the axis, we always want a positive value. So when we want to find some optimized value of z, there's a theorem that tells us the only place you need to look are these intersection points. So we have 0, 8. This one here is 2, 3, and 8, 0, which are pretty easy to find. You just solve 2 linear equations and 2 unknowns, and then you find the value at those points. So for the first one, z is going to be what? It's going to be 24. The second is going to be 4 plus 9 is 13. And for this one, it's going to be 16. So, assuming we wanted to minimize our value here, we can see that at this point here, 2, 3 it's going to be the minimum. So that's a technique called linear optimization. It doesn't matter how many constraints you have as long as they're all linear. This can be very useful in business when you're modeling something like you want to manufacture something and your constraints are, well, you don't have to buy, you have to pay so much for your parts in an order, or you have to buy a minimum number of parts, and you're looking to, say, minimize your cost. So this is a different strategy you could use. We're not going to, this is not part of our class, this is just, fits in with the general topic that I wanted to mention. Is there anybody here who's run into this in high school before? Oh, okay, well, maybe it's gone out of fashion. All right. Okay. So now we're getting to, excuse me, the meat of the matter here. We want to talk about nonlinear optimization. And this is best addressed by looking at some example problems. So the first problem involves putting up a 3-sided fence. Maybe this third side is a river. I guess the book chooses that. I like to think, well, maybe there's a wall there. Uh-oh, we could get into politics here, couldn't we? This could be the Mexican border. We put up a wall. But we have, for this fencing material, 2,400 feet of material. And what we want to do is we want to create the largest area possible. Maybe we've got some cows who want to graze on grass, and we want to give them as much room as possible. So we need a way to go about this. Well, it would help if we give the size of this rectangle here some names. So we'll call the width x and the length y. And then we can form some equations that describe this. Clearly the perimeter is 2x plus 4, and that's 2,400 feet. See if you people have in a little later. I'll hand out, there's a few other homeworks I want to hand out, but I did want to note someone turned in a nice paper with no name on it. I think you might have done this, I guess, come out during the break or after class and name it so you can credit for it. All right, and the area, of course, is just x times y. And the area, of course, is what we want to optimize or maximize in this case. So how would we go about that? Well, it certainly would help if we have an equation or formula for the area, but just in terms of one variable. And since we have two equations and two variables, we know we can get that. Right? So what we'll do here is we'll solve for y. And we'll then substitute it in here. equals x times 400 minus 2x, or a equals 2400 x minus 2x squared. And it might be nice at this point to kind of reference a as now a function of x. So if we want to maximize a k of x, what would the obvious thing to do here? This is a polynomial equation. Doesn't really matter. It could be any function. What do we do when we want to find a maximum or a minimum?
Set the derivative to 0. Set the derivative and equal to 0.
Set the derivative equal to 0? Sure, that's the usual way we go about this. So let's find the a dx. That's 2400. Minus 1x. We'll set that equal to 0. And we solve it. This is going to give us x equals 600. Well, x is 600. Y is 1200. And our area will be just 72000 square feet. Okay, that's a real basic, straightforward kind of problem. We're going to have to look at similar but progressively more complicated problems. Okay. This is a similar idea, but a little more complicated geometry. Certain windows, I think we'll call these Norman windows. I've never run into that name before. They're a rectangle with a circle on top. We've all seen these. I guess, well, if you look over yonder, they're not quite Norman windows because they're separate windows. But we do have that same form, circle on top and a rectangle. And of course, we have some constraint here, which is the perimeter has to be 16 feet. That's, there's a metal band we want to put around the window. And we want to maximize this. Maximize the area, how much light you can get through it. So if r is the radius of our circle, this side here is obviously going to be 2r with diameter, and we have some height here that's unknown. So we want to just start writing down some things we know from geometry. So the area of the circle, is a full circle, would be pi r squared. But the area of the semicircle is just going to be pi r squared over 2. The area of the rectangle, well, that's just length times width, so it's 2hr. So the total area is just this sum, 2hr plus pi r squared over Now we have this problem, we have two variables here. We have r and h. We'd rather just have one, but we have another constraint, which is that the perimeter is 16 feet. So how would we figure that out? Well, we've got two h's and two r's. And we have the circumference, the semicircle length of this. Well, so the circumference of the full circle would be pi times the diameter, or 2r pi. But since this is half, it's just going to be pi r. And that's equal to 16. Well, that gives us another equation that we can use, another equation in the same two unknowns, so we can eliminate one of the variables. In this case, it's probably best to eliminate h. We can solve for h pretty easily. 2h is going to be 16 minus pi r minus 2r, and then we're just going to divide by 2. And we'll get h equals 8 minus pi over 2r minus r, or this might be handier, 8 minus, what have we got here? Pi over 2 minus 1. I think I did something wrong again. Oh, because this would be plus. I'm going to step back here, sorry. I don't really want to divide by 2. I mean, just for practical reasons. Because when I substitute in, I've got a 2h here, so I might as well just leave it 2h. Okay, so let me do that. Let me substitute in. So my area now, just a function of r, becomes 16 minus pi over minus 2r times r plus pi over 2r squared. Okay, well, I have a little algebra to do here. So I have 16 r minus pi r squared minus 2r squared plus pi r squared over 2 is 16r minus r squared times what? Pi minus 2 plus pi over 2. Area. Yeah, I think that's just 16r minus r squared 3 pi over 2 minus 2. Okay. So what am I going to do next here? I have a function of area in terms of one variable, and I want to maximize it, I want to optimize it, so it's the same process, right? What's that? What do I do when I want to minimize or maximize a function? Find its minimum or max. And I know you know Lillian, so you can sit this one out. Anyone? Yes, Isabel?
You find the first derivative and set it equal to 0.
That should do it. Thank you. We want to find derivative of the area with respect to R. Someone want to tell me what that is? Well, someone in the front row. I want to find the derivative of 16R minus R squared times 3 pi over 2 minus 2. I know this isn't the most exciting problem in the world. We'll get to that. That's coming later. We have to get our mechanics down here. What do I do with this?
Would it just be 16 minus
16 minus
2R?
2R times this mess, right?
Yeah.
3 pi over 2 is 2. So that's what? 16 minus R times 2 pi minus 4. And what do I do with? I think I made a mistake here. That's a 3. Oh, I know I made a mistake now. Find it. This should be something else. Well, now I have to stop being a teacher and start being math students. So, I have 2 H's plus 2 R's plus pi R. And 2 H's equals 16 minus pi R minus 2R. Well, that's what 2H is, so that times R plus pi R squared over 2. Okay. Where did I go wrong? 16 minus pi R squared minus 2R squared plus pi R squared over 2. 16R, take out the R squared, minus R squared, pi. Well, that's going to be plus, and that's going to be minus. So that's just going to be pi over 2. Okay. Understands, you know, I have the math algebra class, and students often get messed up with the minuses, and I understand why, because if you're not paying attention, that's what happens. Okay. So 2 pi, pi over 2 minus 2 is just going to be pi minus 4. All right. So where we were is we have the derivative, and to find the maximum, we're going to set it equal to
Zero.
Thank you. Thank you. So that just makes R equal to 16 over pi minus 4. Doesn't sound good. Oh. I didn't bring the plus screen. All right. So now we know that to optimize this, we want the radius to be 16 over pi over 4, which is, a little bigger than 2. And if we want to, we could now substitute those values in here, or I guess maybe here, and we can find out the area, the optimized area. All right. Okay. So I know that there are no farmers in this class or window makers. But in a futile attempt to gain your attention, we'll do a problem from business. See what we can get some excitement out of this. So a game console manufacturer, he determines that in order to add markers here. In order to sell X units, everyone here knows what a game console is, right? I don't have to, it would be just kind of stupid if it would be me who doesn't know what that is, but I know what that is. The price, in order to sell these units, the price per one unit, I'm going to play an economist here today. Price per unit must decrease so actually it's price per one unit must decrease by the linear law called the demand function. Okay, let's try and figure out what that means. So we're trying to sell these units and we're going to set some price. So the first one, we can set some high price, but future units, we have to lower the price, so we're not going to sell them. That's what we call in microeconomics the demand curve. The more units you have available, the lower the price is going to go. So we have an equation for that. P of x equals $500 minus 0.01 x per device. Okay, so with each unit we sell, the price gets a little lower. And the manufacturer determines that the cost depends on a volume of production that includes a fixed part, this is production, okay, we're doing big business here, $100,000, and a variable part $100X. x, where x is the number we're selling. That is, the cost function is $100,000 plus 100x. So eventually, once we kind of amortized our startup costs, it's costing us $100 to produce one of these things. Okay, so we've got the cost and how much we can sell them for per unit. So we have a revenue function per unit, which is x times the amount you're going to sell it for, is equal to x times 500 times 0.01x. I think this was a bad choice of, this is lowercase p for price, right? Because we're going to use capital P. This is revenue, profit, this is price per unit, and this is cost. Okay, so what do we want to we're business people, we want to maximize profit, so this is what we're really interested in. The profit is the revenue, how much we bring in, minus our costs. All right, that's pretty straightforward. Let's plug everything in we can here. So the revenue is x, 500 minus 0.01x, minus the cost, which is 100,000 plus 100x. So the idea here is, how many units do we have to sell to maximize our profit? So I need to go over any of these. I mean, this is a complicated problem from, it sounds kind of complicated. And it's hard, it's simple. You're making something, it costs you money. You're selling it, you get so much. But the more you make, the lower the price goes down. So at some point, you're going to break even. It's going to not make sense to make anymore because you won't make back what it's costing you, right? So where is that peak in profit? How do we find that? Well, it's the same thing. You want to find the derivative of the profit with respect to x. This is p of x. Okay, how do we find this? X's, we know how to do that, don't we? Let's rearrange this a little. This is 500x minus 0.01 squared minus 100,000 minus 100x. So it's really 100x minus 0.01 x squared minus 100,000. Still on p of x. Okay, so maybe I should write it this way: negative 0.01 x squared plus 400x minus 100,000. It's more kind of standard form. Okay, so how do we go about finding where the profit is maximized? Is this too simple? Is it too hard? So the derivative I get is negative 0.02x plus 400. And I want to set that to 0. So I'm going to end up with 400 equals 0.02x, or x equals 400.02. It's just going to be 20,000 units. Okay, and you can plug that back in here and find out how much my revenue is. Questions about this example? Yes.
How do you know that's not the minimum and that's the maximum?
Excellent question. How do we find out if that critical point is at a minimum or a maximum? I didn't do that, did I? It could be, well, it would seem, this is irrelevant, but it would seem odd that after selling all these products, I'm somehow like making less. It could be. And that would suggest later on, if I keep making them, I'll start making more. And there may be no maximum. I may just go off to infinity, right? The more I sell. What's our strategy for finding out if a critical point is at a maximum or a minimum? We have actually two ways to do it. Yes? Okay, that's one way. I actually prefer that in this case. Let's find the second derivative. Okay. When the second derivative is negative, what's happening? That means your derivative is getting less and less and less, which means you have a maximum. You could use the first derivative test, in which case you take a point on one side and on the other, and you'd see what was happening to it. And that works even if your critical point isn't, it's not on a continuous curve. If we had an absolute value function. But in this case, the best way to do it. Okay, thank you. All right. Let's try another one of these geometry problems. If you are weak on this part of geometry, you probably need to look into that. Again, I'm happy to go over any of these. Errors. Okay, so this problem is a little more, again, it's more abstract. We take again, we're going to take a semicircle. and we're going to inscribe a rectangle in it. And what we want to know is, what's the area of the largest rectangle we can inscribe? Now, just as a thought experiment, how do we know there is a maximum? Well, imagine we take rectangles that are, closer and closer. The endpoints are closer and closer to these vertices here. Obviously, the areas get smaller and smaller and goes to 0. On the other hand, if we take a rectangle like this and we move these points closer and closer, we're going to get to 0. So assuming this is a smooth continuous function, our intermediate value theorem tells us that between 0 and 0 there must be some maximum. So how do we go about this? Well, we're not given any numbers, so we're just going to say we have, the radius, and that should be all we need to know. Even if we just represent it algebraically, abstractly. Well, one way to look at this problem is, let's think of this as a circle graphed on a graph, in which case we know that x squared plus y squared equals r squared, or at least we should know that. So if we label one of the vertices x comma y, the other vertice will be negative x comma y. And what will be the area of the rectangle? This is where the geometry comes in. You have to kind of look at it and think about it. Let me take a look at that. It really has nothing to do with r, right? It's constrained by r. X can't be greater than r. It has to be greater than 0. Y, again, can't be greater than r. Again, it has to be, it could go down to 0, but get very close. Gets to 0, it's not a rectangle. Yes?
Wait, is it 2x y?
2xy. Does everyone see that? Distance here is x. Distance here is x. Distance here is, I'm not drawing these very well. Y. Okay. Step 1, good. Most of these problems, if you just figure out that first piece there, you're almost there. But of course, now we have the area in terms of 2 variables, which is obviously a problem. But we know all the points here are constrained by this equation. So we could solve for one of these variables and eliminate. So if we say y squared equals r squared minus x squared, we get y equals the square root of r squared minus x squared. And we don't have to worry about this being negative because we're interested in positive distances. So we have 2x square root r squared minus x squared. And that's our function of x. At this point, it's just calculus mechanics, right? We want to find the derivative, set it to 0, and see where the maximum is. Okay. Oh, everyone knows the answer. What's the first step here? What rule do I need to use? Get going. Yes, product rule. I multiply x times this mess, so, all right, good. So x times, I'm just going to write this derivative of square root of r squared minus x squared plus r squared minus x squared square root times the derivative of x, which is 1. Make sure I keep my 2 outside of everything. All right, r squared minus x squared, square root of it. Well, that's kind of like 1/2 r squared minus x squared to the 1/2. So I want to find the derivative using the power rule. So that's 1/2 r squared minus x squared to the negative 1/2. But then I have to continue with my chain rule and find the derivative of r squared minus x squared, which is, the r squared goes away, it's 0, it's a constant, times minus 2x. This is going to get messy, so have lots of paper ready. So a prime of x equals 2 times x times this. Well, 2's cancel, that's nice. Negative x over square root minus x squared. Wait a minute. Yeah, what's this? Okay. Are we good with that? Anybody checking my work? I'm feeling insecure. X times the derivative of this is this. Okay. Derivative is 1/2. Negative 2x. Cancel. So we end up with 2x negative x over r squared plus that. Okay. I'm happy. And we just do the same thing we always do. We set this equal to 0 and figure out what to do with it. No idea. It sounded exciting. You can have like a flash mob out there, right?
There's like a dance performance thing with all the classes during
Okay.
during dead hour, so they're all dancing out there.
Oh, well, that'd be exciting. Okay. All right. We're setting it equal to 0, so we can divide by 2. That goes away. My intuition is put this over a common denominator. Yeah, okay. So x times negative x over square root of r squared minus x squared. Well, I'm going to multiply this by r squared, square root of r squared minus x squared over square root of r squared minus x squared. So on top, I'm just going to get r squared minus x squared. Now, I know, except they are, which doesn't make any sense, right? That would be, remember our problem, that would be x equal to r. That's, we know it's going to, area is going to be 0. We know this is a non-zero value. So again, we can just get rid of it. We get negative x squared plus r squared minus x squared equals 0. Now it gets easy. Negative 2x squared equals negative r squared. So these positive x squared equals r squared over 2. Or, of course, x is going to equal plus or minus the square root of 1/2 r. Oh. Well, that's interesting. Draw this nicely. That means this is r. This is r over 2. That's going to be my maximum area, which is going to have what? It's going to have size of r, so the area is going to equal r squared. That's kind of cool. We didn't have to pick an r, did we? Is true of any circle. Well, if you know the radius, you know the area, the maximum area of an inscribed rectangle, which appears to be a square. It's just kind of a feature of math many times when you're trying to maximize something, that some symmetry kind of works its way in. I mean, it's no surprise that, well, in this case, it has to be that each side, on each side of the axis is going to have the same area, but that the length and width are the same. It's a little surprising. Okay. Well, we can do just a geometry problem in an abstract manner. Maybe we can do a business problem that way too. So, again, this is just my background. I'm more familiar with math, getting contours, but I know in business, sometimes you just get handed a formula. It's not that somebody derived the formula. It's more typically they did an experiment. They did some statistics, they collected data, and they come up with a formula. I don't think that's true of this one. I think they just made this up because it creates a reasonable problem. But so for this problem, we have the production cost for a period of time is given. We don't even know what it is. Right? What are we building here? The bubble gum or submarines. We're just given that the cost to produce this item per unit time, we should have use T. Might make more sense. There's some fixed cost, that's our A, and then as time goes on, apparently production cost increases. I mean, this probably starts out small. found this in a book, but just trying to think, does this make sense? Well, maybe I'm not understanding the problem, the economics of the problem. Because it does seem after a certain period of time, it's going to be really expensive to make. If we're adding, even if B starts out small, it's going to get big at some point. Well, oh, you know, it could be, here's a good example. Anyone think of an example of something like this? Just thought one. Oil extraction. Everyone know what's going on today in oil? Price of getting oil is going up. I heard a guy talking on the news. He was saying today, for every 100 barrels of oil we extract, it takes 15 barrels of oil to get that 100 barrels of oil. So we're only getting 85. And within a few years, it'll be 25%. And by 2050, it'll be 50%. That is, for every barrel of oil we end up with, we're going to have to, extract 2 barrels. So it's getting very, very expensive. I think that's what this is recognizing, is something that as time goes on, it gets more expensive. Okay. I just wanted to satisfy myself this is not a crazy problem. It makes some sense. Okay, so what we want to do is find the minimal average cost. That is cost, average cost is the cost per unit. So, okay, so they use the syntax, the little bar means the average. So the average cost is the cost over the number of units. And we see that that's A plus, well, we're going to use T, so T will be consistent. Oh no. Okay, wait a minute. So I was wrong. This is just per unit, not per time. Kind of the same thing, as we do make more and more, time goes on. Okay, my mistake. I had it right. Okay, so this is A plus bx squared over x, or A over x plus bx. That's our average cost per unit. And we want to find the minimum of this function. So what do we have to do? We have to find the derivative, the average of x. And what's the derivative of a over x? It's obviously going to be a times something. Derivative of x to the n is x to the n minus 1. So here x is, here n is minus 1. So derivative of x to the minus 1 is minus 1x to the minus 2. So it's just negative ax squared plus bx. And of course, to find the critical points, we want to set that to 0. Multiplying through by x squared, we get minus a plus bx cubed equals 0. Or bx cubed equals a, x cubed equals a over b, or x equals the cubed root of a over b. Did we do that right? And so if we want to find this value, c of cubed root of a over b, we just have to plug it in. It's a plus b times cubed root of a over b squared over cubed root of a over b. So that's the value at the critical point. The question comes up, is that a minimum or a maximum? So we want to find the second derivative. Second derivative of a over minus a times x to the minus 2 is going to be 2a x cubed plus b. And since a and b were presumably positive, that shows this is a minimum. Yes?
Isn't in the first derivative, shouldn't it just be plus b?
Where are we?
First derivative, shouldn't it just be plus b?
Yeah, I was wondering why it came out different here. Let's fix that. Okay. So what happens to this? Oh, well, wait a minute. Second derivative. Huh. Oh, well, that's going to be positive because the number of units has to be positive, right? So it's the same answer. Thank you. Yes?
I think also for the first derivative, I think it's negative a over x, not x squared.
The derivative of a over x is, I'm saying it's negative a over x squared. And you think it should just be a over x?
No, negative a over x.
Oh,
Unless
wait. This is what we're talking about, right? Derivative of a over x, which is a x minus 1. So this tells me it's negative a x, negative 1 minus 1 is minus 2.
Ah,
Okay? I do appreciate you pointing it out, even if there seems to be a good chance with these things that I've got them wrong. Being a little neurotic here, but we could, this is squared, so this is a over b. If the b goes away, so it's 2a times the square root of b over a. Which you can write as 2 times the square root of ab. That's nice. one more. I want to do one more problem. It's a little different. It's a, it's a geometry problem again. But we're just looking at kind of typical problems, like might be in homework exam. The process is almost always the same, but the geometry, or in the case of the business ones, understanding the components can be a little different. So I have this curve, kind of looks like this, and it is f of x equals x to the 3/2. And I have a point 1/2, 0. And I want to find the point on this function that's closest to this point. Now I have to be a little careful because I'm not interested in well, there really isn't any part of this graph over here, but the math may show up with some point over here. May not realize that since I have to find a square root, I can't find the square root of a negative number. So the domain of this thing is just x greater than or equal to 0. So does anyone remember the distance formula using points? I have x1, y1, x2, y2, and I want the distance between these. Does anyone remember the formula? I think you'd probably do this in geometry. Let's call it analytic geometry, or coordinate geometry. Or you might figure this out looking at you have 2 points. You might think of a right triangle and the Pythagorean theorem. Well, this is y2 minus y1, and this is x2 minus x1, and this is my my hypotenuse. This is, again, in calculus, we're all we know the rules here. We can do it or can't. But it's the geometry that makes these problems a challenge. Can anyone tell me what h is equal to here? All right, I'll take that as a no. Can anyone tell me what the Pythagorean theorem tells me? Alright. So A and B are the legs and C is the hypotenuse. So that means h squared equals x2 minus x1 squared plus y2 minus y1 squared, or h equals square root of x2 minus x1 squared plus y2 minus y1. This is sometimes called the distance formula, and it's what we need for this problem here. We have 2 points. One of them we know the coordinates. For this, we know the coordinates are x and x to the 3/2. And we want to minimize the distance using the distance formula. So let's try that. So the distance, hypotenuse of mine is square root of x2. x2 is, let's say, x to the 3/2 minus x1, which is 1/2 squared, plus y2, which is, okay, I just write x minus a half, isn't it? No. Oh, such a long distance. This is x minus. How did I write this wrong? It's not going to come out very nice. Yeah. I'll just have to ignore what I wrote and do it the right way, I guess. Okay, so it's y2 minus y1. No. I need to do this more now. I'm not used to it, but you can learn something from this, right? You just be very, very careful about this. It's like x1, y1, x2, y2. So x1, x2 minus x1 is x minus half. Similarly, y2 minus y1 would be x to the 3/2 minus 0. Okay. Now I can do this properly. So x minus 1/2 squared plus x to the 3/2 minus 0 squared. Okay. Oh, that was the tricky part. There's one more thing. You know, you can be smart about this. It's like, I'm going to find the derivative of this. This is going to be an ugly mess, or it's going to be more work than I need to. If I'm trying to minimize this distance here, I can just as well minimize its square. I'll get the same thing. Right? So we'll have some, we'll call it d squared of x. X minus 1 squared plus x to the 3/2 squared. And we'll try and minimize this, and it'll work this as well. So let's, oh goodness, you're going to have to speed this up. X squared minus x plus a quarter plus x cubed. I'm going to find the derivative of this. 2x minus 1 plus 3x squared equals 0. And this is a quadratic we can solve, find the value, and check to make sure it's a minimum. All right, thank you.